Lesson 15, Exponential Decay. Exponential decay is any pattern of decay by which decay occurs at an ever-increasing rate. So exponential decay is any pattern by which the decay occurs at an ever-increasing rate. In an equation involving exponential decay, a value is constantly multiplied by a number greater than 0 but less than 1. So in an equation involving exponential decay, a value will be constantly multiplied by a number bigger than 0 but less than 1. Just like in a function involving exponential growth, you can identify a function involving exponential decay when given a set of ordered pairs because the ratio of consecutive finite differences is the same. Just like in a function involving exponential growth, you can identify a function involving exponential decay when given a set of ordered pairs because of the ratio of consecutive differences will be the same. It is important to know that all finite differences exhibit this property. So all finite differences will exhibit this property, that consecutive finite differences will be the same. You will be easily able to identify the graph of an exponential decay because as the independent variables increase, the dependent variables becomes exponentially smaller. So you can identify an exponential decay graph because as the independent variables increase, the dependent variables become exponentially smaller. The following is a graph of a function involving exponential decay. This is the graph of a function involving exponential decay. And as you can see, it starts big and it goes smaller and smaller and smaller. So as the independent variables increase, these values, the x values, as they increase, the dependent variables become exponentially smaller. And it goes on forever in both directions. Now let's review the different parts of a function involving exponential decay. Exponential decay. This is your exponential function. And as the independent variables increase, the dependent variables become exponentially smaller. And you will notice that for the standard function, it goes from positive infinity, from a value of y value of positive infinity to a y value of 0. But it never touches 0. So there's an asymptote at y equals 0. The variable b is the value of the ratio. The variable b is the value of the ratio between successive dependent variables. In other words, so the variable b is the ratio between successive dependent variables. In other words, this is the value that is multiplied x number of times, thus causing the function to decay exponentially. So b is the value that is multiplied x number of times by itself, causing the function to decay exponentially. For exponential decay to occur, this value must be less than 1. So this value b is always less than 1 in the exponential decay function. For exponential decay to occur. If the value of b is more than 1, exponential growth will occur. So if b is more than 1, exponential growth occurs. The variable x is an independent variable and is used to denote the number of times the value of b is multiplied by itself. So the variable x is an independent variable and it's used to denote the number of times the variable b is multiplied by itself. The variable a is the vertical stretch. That stretches or compresses the function by a factor of a. So a is the vertical stretch that stretches or compresses the function by a factor of a. We note that if b has a value of 0, we know that if x has a value of 0, then b raised to the power of 0 is 0. Sorry, b raised to the power of 0 is 1, because any non-zero number raised to the power of 0 is 1, and 1 times a is a. So the y-intercept for an x value of 0 will always be a. So the y-intercept will always be 0a. Before you tackle problems involving exponential decay, it is important that you understand one term. So before we tackle any problems involving exponential decay, we're going to go over one term. The term half-life refers to the time it will take for an unstable element to decay to half of the original amount. So the term half-life will refer to the time it takes for an unstable element to decay into half of the original amount. When writing an equation for a problem involving half-life, the variable b will have a value of 1 over 2, and x will represent the number of half-lives. So when we write an equation for a problem involving half-life, the variable b will have a value of 1 over 2, and x will represent a number of half-lives. When given a specific amount of time, divided by x to find the number of half-lives that have occurred. So when you're given a specific amount of time, divided by x to find the number of half-lives that have occurred. Now let's go through the word problem involving exponential decay. Pu-239, or plutonium, is a radioactive element that has a half-life of 24 years. Determine how long it will take for a 20 milligram sample of plutonium to decay to 1/4 of its initial weight. First, we'll have to create an exponential function to represent the amount of uranium over time. So first, we have to create an exponential function to represent the amount of uranium over time. Let x represent the number of half-lives that have occurred since the plutonium was allowed to begin decaying. So x represents the number of half-lives occurred since the plutonium was allowed to begin decaying. Also let a of x represent the amount of plutonium left after x half-lives. Also, we let a of x represent the amount of plutonium left after x half-lives. Now let's determine what values the different parts of the function will have. The value of a represents the initial amount of the plutonium. Therefore, let a have a value of 20. Since the value of a represents the initial amount of plutonium, and we're told that we start with a 20 milligram sample, we let a have a value of 20. The value of b represents the factor that is multiplied x number of times. So the value of b represents the factor that is multiplied x number of times. Since plutonium decays to half of its amount, let b have a value of 1 over 2. Since plutonium decays to half of its amount, let b have a value of 1 over 2. Consequently, the equation of the function is a of x equals 20 times 1/2 raised to the power of x. So the function is a of x equals 20 times 1/2 raised to the power of x. Now we must determine the value of a of x, or the amount of plutonium left after any decay. So now we have to determine the value of a of x, or the amount of plutonium left after any decay. Since the problem tells us that 1/4 of the initial amount is left after the decay, let a of x have a value of 5. So because the problem tells us that 1/4 of the initial amount is left after the decay, and 1/4 of 20 is 5 milligrams, let a of x have a value of 5. So we substitute 5 into the function and we solve for x. 5 equals 20 times 1/2 raised to the power of x. We need to isolate x, so we divide both sides by 20. So here we need to isolate x, so we divide both sides by 20. We get 0.25 equals 1/2 raised to the power of x. Now you must determine how many times 1/2 is multiplied by itself to get 0.25. These are calculator if you need it. So we have to determine how many times 1/2 is multiplied by itself to get 0.25. We use a calculator if we need it. To do this in a calculator, you would take the logarithm of 0.25, the logarithm of 1/2, and because x is an exponent, you write it in front of logarithm of 1/2, and then you divide the logarithm of 0.25 by the logarithm of 1/2 by the logarithm of 0.5, and you get 2. So again, you take logarithm of 0.25 divided by the logarithm of 0.5 to get x. So x equals 2, because 1/2 times 1/2 equals 1/4, or 0.25. 1/2 times 1/2 is equal to 1/4, or 0.25. Therefore, the plutonium decays to 1/4 of its original amount after 2 half-lives, or after 48 years. So the plutonium decays to 1/4 of its original amount after 2 half-lives, or after 48 years. We know that 2 half-lives are 48 years because in the problem it tells us that 1 half-life is equal to 24 years. Since you will encounter problems involving negative exponents, it is important that you learn how to perform operations involving negative exponents. Because you will encounter problems involving negative exponents, it's important that you learn how to perform operations involving negative exponents. When a value is raised to a negative exponent, simply place the value under 1 while keeping the absolute value of the exponent. So when a value is raised to a negative exponent, simply place the value under 1 while keeping the while keeping the absolute value of the exponent. The formula for operations of this type is a raised to the power of negative n equals 1 over a raised to the power of n. So remember, when a value is raised to a negative exponent, place the value under 1 while keeping the absolute value of the exponent. So a raised to the power of negative n equals 1 over a raised to the power of n. Let's go through a few examples. 6 to the power of negative 3 times 6 to the power of 2. First, apply the product rule by adding the exponents because the bases are equal. So because 6 is equal to 6, we can add the exponents. Negative 3 plus 2 is negative 1. So 6, we get this equals 6 to the power of negative 1. We apply the negative exponent law. This is equal to 1 over 6 to the power of 1, or 1 over 6. Here we apply the negative exponent law, because we have a negative exponent plus a negative exponent. So we apply it to both of them. Equals 1 over negative 2 to the power of positive 4 plus 1 over 4 to the power of 2. Positive 2. 1 over negative 2 to the power of 4 is 1 over 16 because negative 2 to the power of 4 is 16. And 1 over 4 to the power of 2 is 1 over 16 because 4 to the power of 2 is 16. 1 over 16 plus 1 over 16 equals 2 over 16. Now that you know how to use the negative exponent law, you can simplify expressions involving negative exponents. So now that you know how to use the negative exponent law, you can simplify expressions involving negative exponents. So here we have an expression involving negative exponents. What we do is we first look and we see that all of these exponents have the same base. So we can add the exponents. Apply the product law by adding the exponents. So we do -2 plus -3 is -5, plus 4 is -1. So we get x to the power of -1. Same base, we just add the exponents. This is a negative exponent, so we simplify it. We get 1 over x to the raised to the power of 1, which is equal to 1 over x. Lastly, you need to know how to work with rational expressions or fractions that involve negative exponents. So lastly, you need to know how to work with rational expressions or fractions that would involve negative exponents. When a fraction is raised to a negative exponent, simply raise the reciprocal of the fraction to the absolute value of the exponent. So when a fraction is raised to a negative exponent, simply raise the reciprocal of the fraction to the absolute value of the exponent. Let's go through an example. So we have a fraction with a negative exponent. We apply the negative exponent formula. Convert the base to its reciprocal. So we apply the negative exponent formula on this fraction. Convert the base to its reciprocal and raise it to the absolute value of the exponent. So what we do is convert the base to its reciprocal and raise it to the absolute value of the exponent, which is -2. So the reciprocal of -2 over 3 is 3 over -2, which is the same as -3 over 2. And we raise that to the absolute value of the exponent. The absolute value of -2 is 2. Raise the numerator and the denominator to the value of the exponent. So now we raise the numerator and denominator to the value of this exponent. So we square -3 and we square 2. -3 squared is 9, 2 squared is 4. So we get 9 over 4 as our answer. That's all there is to exponential decay. Next we'll learn about rational expressions. So that's all there is to exponential decay. Next we'll learn about rational exponents. And that's all for lesson 16, exponential decay. Stay tuned for lesson 17, rational exponents. If you like this lesson, be sure to give it a like and a thumbs up, and also leave a comment down below. Thank you.